Welcome to Learn with me. These notes summarize key ideas in data analysis, starting with statistics and its foundation, probability. Please note this is my personal note, not an official lecture. Okay, let's start with important concepts of probability. First, outcome. An outcome is the result of a single trial of an experiment in probability. For example, if I flip a coin once, there are two possible outcomes, heads or tails. Or in the case of a loan or a bond, there are two possible outcomes, either default or no default. Next, event. An event is a single outcome or a set of outcomes. For example, if we roll a die, an event could be rolling an odd number, which includes three outcomes, 1, 3, and 5. If an event consists of only one outcome, it is called an elementary event. On the other hand, if an event contains no possible outcomes, for instance, rolling a number greater than 6, it is called the empty set or the impossible event. Next, population. A population refers to the entire group that we are interested in studying. For example, the population could be all the people living in a particular state. However, if we want to conduct a survey, say, to measure IQ, it is usually not possible to test every single individual in the state. Instead, we select a smaller group, such as 1,000 people. This smaller group is called a sample. The sample is used to represent the population, so that we can make inferences about the whole population without measuring everyone. Random variables can be divided into two main types. Discrete random variables. These take on distinct, countable values. The range of values may be finite or infinite, but in either case it is countable. Example: the number of students admitted to Harvard in a given year. Continuous random variables. These take on values from an interval of real numbers. Their values are uncountable. Example: a person's height or weight. Sample space is just all the possible outcomes of an experiment. For example, if we roll a standard 6-sided die, the sample space I/S equals 1, 2, 3, 4, 5, 6. The event space refers to the set of all possible events that can occur, based on the sample space. Each event is a subset of the sample space, and the event space is the set of all those subsets. Let's look at a very simple case with just one bond. The sample space has only two outcomes. Either the bond defaults, or it does not default. Now, the event space is the set of all possible events, which means all subsets of the sample space. In this case, it includes default, no default, default or no default, which is the certain event, and the empty set, which is the impossible event. So even in this very simple bond default example, the event space contains 4 possible events. And in general, if the sample space has n outcomes, then the event space will always have 2 to the power of n possible events. Now that we've defined the event space, let's talk about probability. Probability is simply a way to measure how likely an event is to occur. By definition, probabilities are always between 0 and 1. An event with probability 0, then it never occurs, which means it's impossible. An event with probability 1, then it always occurs or it's certain. Probability itself can be interpreted in two different ways, objectively and subjectively. From the objective point of view, probability comes from experiments. You simply count the frequency of an outcome when the experiment is repeated many times. This is called the frequentist interpretation of probability. On the other hand, from the subjective point of view, probability reflects a person's beliefs about how likely an event is to occur. These beliefs may differ from one individual to another and don't have to match the objective probability. For example, a senior executive might assume a specific probability for a future event, like a recession, an interest rate increase, or a credit rating downgrade, when running scenario analyses or stress tests. That's a subjective probability, based on judgment rather than repeated experiments. Now let's look at how probabilities work when we deal with sets of events. The first relationship is the intersection. This is the probability that both events occur at the same time. We denote this as A and B. Next is the union. This is the probability that either A or B occurs. We denote this as A or B. You can think of the union as combining the two sets. To calculate the probability of A, union, B, we add the probability of A and the probability of B, then subtract the intersection to avoid double counting. The third is the complement. The complement of A, written AC, is simply the set of all outcomes that are not in A. For example, if A is rolling an even number on a die, then AC is rolling an odd number. Now, when we look at the complement of a set, its probability is simply 1 minus the probability of the set itself. In other words, the probability of not A is equal to 1 minus the probability of A. And finally, we have mutually exclusive events. These are events that can never occur together. In other words, their intersection is empty. And the probability of their union is just the sum of their individual probabilities. Now let's look at the three basic axioms of probability. The first axiom is that probability is never negative. For any event A, we must have probability of a greater or equal to 0. The second axiom is that the probability of the entire sample space, which we call omega, is equal to 1. That means if we add up the probabilities of all possible individual outcomes, the total must be 1. And the third axiom is about mutually exclusive events. If we have a collection of events that cannot occur at the same time, then the probability of their union is simply the sum of their probabilities. Together, these three axioms form the foundation of probability theory. Now let's look at two important properties of probability. The first property is about complements. For any event A, the probability of A plus the probability of its complement must equal 1. That makes sense, because either A happens or it doesn't. Together they cover the entire sample space. The second property is the rule for unions. The probability of A or B is equal to the probability of A plus the probability of B, minus the probability of A and B. We subtract the intersection to avoid double counting the overlap. Now let's get into more details with probability of events. When we analyze two events, there are three key factors we need to consider: whether they're conditional or unconditional, whether they're dependent or independent, and whether they're mutually exclusive or not. These factors shape how we calculate probabilities. The most general case is when events are unconditional, dependent, and not mutually exclusive. So let's begin by exploring this with an example. Imagine there's a gentleman who has a crush on a beautiful lady. He's thinking of asking her out on a date, and, being a master of probability, he decides to calculate the chance that she could actually become his girlfriend. He estimates there's an 80% chance that she likes him, which means there's a 20% chance she doesn't. Now, he considers what might happen if he asks her out. If she likes him, he believes there's a 90% chance she'll agree to the date and a 10% chance she won't. On the other hand, if she doesn't like him, he thinks there's still a 30% chance she might agree, maybe out of politeness, and a 70% chance she'll decline. Let's now describe this in probability notation. The probability of like is written as P of L, equal to 80%. The probability of not like is written as P of LC, which means the complement of like, and that's 20%. These are unconditional probabilities. They stand alone and don't depend on any other event. Now, the probability of date is different. The 90% here is not just the probability of date by itself. It's the probability of date given that she likes him, written as P of D given L, equal to 90%. Likewise, P of not date given L is 10%. Similarly, if she does not like him, the probability of date is 30%, so P of D given not L equals 30%, and the probability of not date given not L is 70%. Because all of these depend on whether like or not like happens, we call them conditional probabilities. Now let's look at the probability tree we have here and calculate the probability of both events happening together. The chance she likes him and agrees to the date is 80% times 90%, which gives us 72%. The chance she likes him but cannot go to the date is 80% times 10%, so that's 8%. The chance she doesn't like him but agrees to date is 20% times 30%, which comes to 6%. The probability she doesn't like him and doesn't agree to date is 20% times 70%, making it 14%. These are joint probabilities. Now look carefully at the first one. The probability of like and date equals 80% times 90%. That is, the probability of like multiplied by the probability of date given like. And this is what's called the multiplication rule for probabilities, and here's how it works. The chance that two events both happen is the chance of the first event happening multiplied by the chance of the second event happening, given that the first one has occurred. Now let's reorganize this into a joint probability matrix. We'll put the rows as date and not date, and the columns as like and not like. From our probability tree before, we can fill the cells like this. Date and like is 72%, date and not like is 6%, not date and like is 8%, not date and not like is 14%. Now, look at the column totals. If we add the like column, we get 72 plus 8, which is 80%. That matches our original assumption. Similarly, the not like column adds up to 20%. Then, look at the row totals. The date row adds up to 72 plus 6, which is 78%. That's the overall probability of getting a date, unconditionally. The not date row adds up to 22%. So now, if we look at both the tree and the matrix together, we see the probability of date. From the matrix, we already know it's 78%, which comes from 72 plus 6. And we could see, 72 is the result of probability of like times probability of date given like. And 6 is probability of not like times probability of date given not like. So we can write it like this. The probability of date equals the probability of like times the probability of date given like, plus the probability of not like times the probability of date given not like. And this is the total probability rule. From our example, we can now generalize. This is the general formula of the law of total probability. To continue, let's keep going with the example. He finally sent the message to ask her out, but she says no. Now he is sad, and he begins to lose confidence. He no longer thinks that the chance she likes him is as high as the 80%. So he wants to recalculate this chance. At this point, his world has shrunk down to just the situation of no date, which overall happens 22% of the time. Within that 22%, 8% comes from the case where she did like him but still didn't go, and 14% comes from the case where she didn't like him and didn't go. So now, given that there was no date, the probability that she liked him is only 8 out of 22, about 36%. His belief has been revised. Similarly, probability of she does not like him is around 64%. And this is exactly what Bayes' rule is about. It's the idea of starting with an initial belief, then updating it once we get new information. More generally, Bayes' rule says that the probability of something, given new evidence, equals your prior belief times how consistent the evidence is, divided by the overall probability of that evidence happening. So far, we've seen the general case, unconditional, dependent, and not mutually exclusive. That's where we needed the multiplication rule, the law of total probability, and Bayes' rule. Now let's see how these formulas change in other situations. The next combination is when the events are unconditional, independent, and cannot be mutually exclusive. So what's different in this case? The key is that the events are independent. What does that mean? In our example, it means that the event date no longer depends on the event like. In other words, whether she likes him or not doesn't affect her decision to go on the date, she always gives a chance. So the probability of date is 90%, and not date is 10%, in both cases. Which means the probability of date given like equals the probability of date given not like and equals the probability of date. Similar to the probability of not date. The multiplication rule then simplifies. Instead of writing probability of A and B equals probability B times probability of A given B, we just write equals to probability of A times probability B. In other words, for independent events, we can drop the conditional part. The next combination that the book of FRM Part 1 mentioned is unconditional, dependent, and mutually exclusive events. The main difference from our first example is that now the events are mutually exclusive. Let's go back to our story of the gentleman. Two events are mutually exclusive if they can never happen together. So for example, suppose the lady is extremely careful with her time. If she does not like him, she will never waste her time going on a date. That means the events, not like, and date, are mutually exclusive. They can never occur at the same time. So in this case, if she doesn't like him, the probability of date is 0, and the probability of not date is 100%. Which means probability of date given not love is 0. So the multiplication rule becomes very simple. The probability of A and B is just 0. And the probability of A or B is simply the sum of their individual probabilities. The last combination we need to understand is conditional independence and conditional dependence. The main difference from the earlier examples is this idea of being conditional, meaning the relationship depends on some given information. So, what can we add to our original example to make it conditional? As we mentioned before, the probabilities of like and not like were unconditional. They didn't depend on anything else. But to make it conditional, we need to introduce some new information, something that the probability of like could depend on. Now, let's add another condition. Suppose the gentleman is poor, and the lady may or may not be materialistic. Which means in our probability tree, before the like and not like events, We now introduce two new branches, one for a non-materialistic woman, and one for a materialistic woman. If she's not materialistic, then nothing changes, all the probabilities remain the same as before. But if she is materialistic, then the probabilities shift. In that case, the chance she likes him drops to 60%, and the chance she doesn't like him increases to 40%. Also, in this case, the chances of going on a date change too. Since she's likely to go on a date if she can, the probability of going on a date becomes 90%, whether she likes him or not. That means the probability of not going on a date is just 10% in both cases. So now we can see that the probability of like is conditional. It depends on whether the woman is materialistic or not. Given that she is materialistic, the events like and date are independent. She goes on the date regardless of whether she likes him. But if she's not materialistic, then like and date become dependent. Whether she goes on the date depends more on whether she actually likes him. Now let's move to the formulas for the conditional case, independent events. Start with the normal multiplication rule. For any two events A and B, the probability of A and B happening together is P of a given B times P of B. But if A and B are independent, then the conditional part drops out, and we just have P of A and B equals P of A times P of B. Now, when we add another condition, say C, the formula becomes probability of A and B given C equals probability of A given C times probability of B given C. And that's the last case. Now let's look again at the formulars. So basically, these are the most important formulas, and they can be applied in all kinds of cases. Now let's take a look at some example. Our first example is about systemically important financial institutions. Let's say there's a 99% chance that all the institutions are doing fine, and only a 1% chance that at least one will go bankrupt. Now, if one institution fails, here are the chances for what happens next. 0% chance that no more institutions fail, 20% chance that one more fails, 20% chance that two more fail, 20% chance that three more fail, 20% chance that four more fail, and 20% chance that five more fail. And the question is, what's the probability of having at least two total failures, given that one failure has already happened? Let's take a look at the probability tree to really see what's going on. First, notice that the question asks about the probability of at least two failures, but it also tells us that one failure has already happened. So really, we're being asked, what's the probability that at least one more institution fails, given that one already has? And that is all the case from one more failure to five more failure, which means 100%. Once the first failure happens, at least one more is guaranteed in this scenario. Now let's look at another example. This time is about mutual fund manager. Suppose in the market, 10% of managers are superstar managers and 90% of managers are non-superstars. For superstar manager, the chance of beating the market in a year is 20%, and the chance of not beating the market is 80%. And for non-superstar manager, the chance of beating the market is only 5%, and not beating is 95%. Now here's the question. If we observe that a manager beat the market this year, what is the probability that this manager is actually a superstar? In this case, we're re-updating our belief about the manager after seeing new information. This is exactly where Bayes' rule comes in. To answer this question, first, let's figure out the total probability of a manager beating the market. A superstar manager beats the market, that's 10% of managers, times a 20% chance of beating the market. So 10% times 20%, that's 2%. A non-superstar manager beats the market, that's 90% of managers, times a 5% chance, and that's 4.5%. So the total probability of any manager beating the market is 6.5%. And in this 6.5%, what is fraction coming from the superstar group? That's 2 divided by 6.5, which is about 31%. So the probability that a manager is a superstar, given that they beat the market, is approximately 31%. We're again asking what's the probability a manager is a superstar, given that they beat the market 2 years in a row. We'll use Bayes' rule again, but this time, we update based on two events, not just one. We can still use the same logic. First is find the overall chance of any manager beating the market 2 years in a row. We have superstar as 10% times 20%, and that is 0.4%, and similarly for non-superstar manager is 0.225%. Now of all the managers who beat the market twice, what fraction are superstars? That's 0.4% divided by 0.625%, which is about 64%. So if a manager beats the market 2 years in a row, there's a 64% chance they're a superstar. That's a big jump from the 31% we had after just 1 year. So you can see, more evidence dramatically increases our confidence. Our first example is about systemically important financial institutions. Let's say there's a 99% chance that all the institutions are doing fine, and only a 1% chance that at least one will go bankrupt. Now, if one institution fails, here are the chances for what happens next: 0% chance that no more institutions fail, 20% chance that one more fails, 20% chance that 2 more fail, 20% chance that 3 more fail, 20% chance that 4 more fail, and 20% chance that 5 more fail. And the question is, what's the probability of having at least 2 total failures, given that 1 failure has already happened? Let's take a look at the probability tree to really see what's going on. First, notice that the question asks about the probability of at least 2 failures, but it also tells us that 1 failure has already happened. So really, we're being asked, what's the probability that at least 1 more institution fails, given that one already has? And that is all the case from 1 more failure to 5 more failure, which means 100%. Once the first failure happens, at least 1 more is guaranteed in this scenario. Now let's look at another example. This time is about mutual fund manager. Suppose in the market, 10% of managers are superstar managers and 90% of managers are non-superstars. For superstar manager, the chance of beating the market in a year is 20%, and the chance of not beating the market is 80%. And for non-superstar manager, the chance of beating the market is only 5%, and not beating is 95%. Now here's the question. If we observe that a manager beat the market this year, what is the probability that this manager is actually a superstar? In this case, we're re-updating our belief about the manager after seeing new information. This is exactly where Bayes' rule comes in. To answer this question, first, let's figure out the total probability of a manager beating the market. A superstar manager beats the market, that's 10% of managers, times a 20% chance of beating the market. So 10% times 20%, that's 2%. A non-superstar manager beats the market, that's 90% of managers, times a 5% chance, and that's 4.5%. So the total probability of any manager beating the market is 6.5%. And in this 6.5%, what is fraction coming from the superstar group? That's 2 divided by 6.5, which is about 31%. So the probability that a manager is a superstar, given that they beat the market, is approximately 31%. We're again asking what's the probability a manager is a superstar, given that they beat the market 2 years in a row. We'll use Bayes' rule again, but this time, we update based on 2 events, not just 1. We can still use the same logic. First is find the overall chance of any manager beating the market 2 years in a row. We have superstar as 10% times 20% times 20%, and that is 0.4%, and similarly for non-superstar manager is 0.225%. Now of all the managers who beat the market twice, what fraction are superstars? That's 0.4% divided by 0.625%, which is about 64%. So if a manager beats the market 2 years in a row, there's a 64% chance they're a superstar. That's a big jump from the 31% we had after just 1 year. So you can see, more evidence dramatically increases our confidence.